So welcome everybody. For you don't know, I'm the head of College of Science and Engineering, so it's my honour to give the opening welcome address for the inaugural for Spyros Karamanos. So Spyros is a professor of structural engineering, and it's that inaugural celebrated. His first degree was in Athens in 1989, and then he completed his PhD at the University of Texas in '93, I believe. And did 2 years military service in the Hellenic Navy, I believe. So you've been in ships for a bit. I assume you were in ships.
Yeah.
And he was a research fellow in Delft, and then he went back to Greece as an industrial design engineer, and then as professor of structural mechanics at Thessaly University. And his speciality is in structural engineering, which is the backbone of much of our industrial infrastructure, as we all know, especially the offshore oil and gas industry. And that's obviously a big slice of the Scottish economy, so that's very important to us locally as well as globally. And as we all know, these sorts of systems are hard to model, especially when they're under stress or when they fail. I assume you'll be talking about that in some depth. So on with the talk. Thank you very much.
Well, I'd like to thank the head of college for his warm introduction. I'd like to thank every one of you that came to this lecture tonight, and especially my friends and family that came from far away. I will make a presentation as a personal journey in structural engineering, and in particular in the world of tubulars. Starts in Athens and ends up in Edinburgh, covering about 50 years. So let's go 50 years back. In Athens, in Paleophylira, which is a suburb in the south part of Athens. That's where I was born, and I stayed until the age of 22, finishing my undergraduate studies in Athens. That's the place I was born. This is a picture of the family in 1981, taken by a very good friend from the Netherlands, and also it was close to the beach, so that was a great opportunity for me to practice my favorite sport, windsurfing. But there was a very important structural engineering legacy in the family, because my father, Anthony Karamanos, he doesn't want to say that very much, but I need to point that out. There was this tradition that was very important for me, and he's a structural engineer specialized in steel structures. Actually, he's one of the most respected engineers in the country and pioneering steel structures in Greece. And that's several of his projects. Some of them are tubular, so this wind tower, and also the badminton building for the Athens Olympics. And this is a little boy in the beginning of the 70s that is admiring his father's works. I attended a French school, and that was important for me, not only to learn the French language, but also to get acquainted with the French culture. And that is very important for my future steps and my general background. In 1984, as is very important in Greece, you need to pass through examinations, nationwide examinations to enter the university. And I decided to go for civil engineering, and in particular structural engineering. And in those exams, I was quite successful, so I got the first place nationwide. So if you get the first place in your school, in those exams, you're in the news. And for those of you that don't know, that cannot read that very well, this is me. This is a famous Greek comedian. These are two famous Greek politicians. After a few years, the first one became prime minister, the other one became president of the republic. But apart from this very important, milestone, I think that's important for my professional career because it gave me a lot of confidence in my future steps. So I entered the university, National Technical University of Athens, and graduated in 1989. And after that, it was the big step to go to the United States for my graduate studies. So Austin, Texas, was the university that I chose. It was a very exciting time for the offshore industry. And being in Texas, there are many chances that you get something in your graduate studies that is related to the offshore industry. The offshore industry at that time wanted to expand to deep water applications, and one of the problems was the integrity, the structural integrity of pipelines to be installed in depths that exceeded 1,500 meters. So I was sponsored by the Offshore Technology Research Center, and the purpose was to develop numerical tools to understand the behavior of those tubulars, of those pipe components under different types of loading, external pressure, and bending, and buckling. Structural instability was our major concern. And we also compared, we had to compare and complement with a test program performed at our university at that time, test by Professor Kyriakidis. Just a bit of background to understand why this was an exciting time. There were plans for expanding hydrocarbon exploitation in deep water, not only in the Gulf of Mexico, but also in other parts of the world like Brazil, Western Australia, West Africa, Southeast Asia. And there was also a great need to transport oil and gas resources from production locations to countries of highest consumption, for example, Africa to Europe. There were many projects in the 80s and in the 90s. I just want to mention two of them which are very important in my opinion. First, the Trans-Mediterranean pipeline connecting Algeria to Italy through Sicily. The water depth was 600 meters maximum, and it was a pioneering project because at that time it was the deepest offshore pipeline in 1983 when constructed. And the other project is a milestone, the Oman-India pipeline that has been designed in the early 90s. It was the most challenging project of its time, probably of all times. A water depth 3,500 meters and the diameter 26 inches, and that motivated unique, innovative research related to structural integrity. Unfortunately, for political reasons, this pipeline has not been performed, but the legacy is still here in the pipeline community. This is a sketch that shows schematically how we install pipelines in deep water. There is a barge that is, the pipeline is there in pieces coming from offshore, and then these pieces are connected one to the other, and then by advancing the barge and launching the pipe, that's how the pipeline is installed. The most critical part for structural integrity is that part here called the sag bend area, where there is, of course, bending. So it is like a spaghetti, of course, but locally there is a lot of bending. So you take a pipe and you bend, and you don't want that to fail. At the same time, you have a lot of external pressure because you are in deep water, and that combination can be very bad for your pipe. So this is what happens to a pipe when you apply external pressure. Instead of having a circular pipe, when it buckles, it becomes flat, and you don't really want this to happen. And then this phenomenon is accentuated when you add bending. Of course, now with the tools we have and all the knowledge 30 years later, we can understand the phenomenon quite well. But at that time, it was really challenging, so that is the reason why I mentioned those times to be very exciting. After my master's was my PhD, again on offshore structures, but not on pipelines. It was similar, it was offshore structures made of tubulars. So we investigated tubular members that were not just tubes, but they had stiffeners. And those stiffeners could be internal or external and have been used in offshore platforms in the 80s. This is the Cognac platform. You see those stiffened tubes to resist external pressure. But then they wanted to go to oil fields that reach approximately 1 kilometer of water depth. So the question is whether this is safe and the tools we have are adequate. So we developed tools, a numerical finite element methodology to deal with this problem, and the sponsorship came directly from Shell, that was responsible for all those platforms. Shell at the time was a pioneer in those deep water platforms. Just to give you a background, these are impressive structures. The size of those, this is the biggest one, the fixed platform that has been constructed up to that time, is the Bullwinkle platform, gets several awards, for example, the AEC Outstanding Civil Engineering Achievement Award, and it is as big as the CS Tower in Chicago. And it's an impressive structure. The most important feature here, apart from all those impressive things, is the natural period, which is 5 seconds, is the period that is vibrating freely, for those of you that are not very familiar with dynamics. And if you go deeper than that, then these 5 seconds become, say, 7 or 10 or 12, and that may coincide with the frequency, with the period of the wave excitation. So if you increase that number, you get resonance with waves, and it's very difficult to stabilize your structure. So the solution to that problem, if you want to go deeper, is the compliant towers, which is a very promising, it was a very promising concept in the late 80s and early 90s for depths of 500 to 100 meters. And there was always a debate between those towers and the floaters. In the late 90s, because they wanted to go more than 100 meters, of course, the floaters dominated the market, but there were several compliant towers that have been constructed. The Baldpate, the Petronius, and also another one most recently in Angola. It is something in between the fixed platforms that we discussed and the floating platforms, and has this advantage of being very flexible, so that you see those 30 seconds of natural period, so you avoid resonance with waves, but from the other side of the spectrum. Our work was mainly to see to investigate the tubular members in the Mars platform for the Mars field at the depth of 900 meters. It was an impressive project, and we took part on that part of the project. We were very happy to be part of that team. It's an impressive structure, designed completely, but finally it was decided to go for the TLP, for a tension leg platform, so it was never constructed. I had also the chance to meet Peter Marshall and work with Peter Marshall. He was the supervisor from the Shell team, and was one of the people behind all those impressive structural systems. I think it was one of the greatest structural engineers of his time. So I became a Longhorn, graduated, and I'd like to acknowledge the contribution of my professor, John Tassoulas. John was always next to me. He was very supportive, a person dedicated to education and research, and his dedication to quality research, and also his attention to details were a very important feature for the quality of my work. Thank you, John. So after spending 2 years in the military as a sailor and then a petty officer, I went to Delft for my postdoc in Steel Structures Group as a research fellow. And that's where I started realizing that the tubular geometry is not so simple. It's simple if you consider each member by itself, but if you combine the tubes together in order to form a structure, then definitely this connection is not so simple, because it's the connection, it's the intersection of two cylinders in space. And that line here is quite complicated. And one of the features that those connections have is that the local stresses are very, very high, much higher than anywhere else. So if you have repeated loading because of waves mainly and wind, that might start cracking, the phenomenon called fatigue. You see a fatigue crack here, and if that develops, then you have problem in your structure. But it was really an interesting topic, and I really want to thank Professor Vardeneur for giving me the opportunity to work in this topic, and that was a very important step in my career. It was also a great chance in Delft to meet with Noel Gresnicht, who is here, and he didn't participate in that particular project, but after that we did a lot of projects together, so it was really an important meeting. After that, I decided to go back to my country. It was '96, and the country was expanding. There were a lot of infrastructure work. So I decided to go to Thessaloniki. And I worked as a structural engineer in Egnatia Odos, a big highway project. I must say that I had a very good time in Thessaloniki. I didn't do much of tubulars. The only tubular was those very high piers that supported the bridge deck. Those piers were impressive, 65 meters, hollow, rectangular section, and there was a 4x4 section. The thickness was about 40 centimeters. Didn't do much of that work, but it was a great experience for me. And Thessaloniki is a great place to be, especially when you're young and you don't have a family. There is a friend of mine that insists that Thessaloniki is the best place in Greece for young people to retire. But after I was dedicated to education and academics, so I decided to follow an academic career. There was an opportunity in Volos in 1999 that I followed, and I believe that's the start of my academic career. Volos is in the area of Thessaly, which is in the middle of the country. It's halfway the distance approximately between Athens and Thessaloniki. And Thessaly is the birthplace of Achilles. So if you see in Troy with Brad Pitt, yeah, starts in Thessaly. And also Volos is the place where Jason started his expedition with the Argonauts to get the Golden Fleece. So it's a place with a lot of history and well mentioned in the Greek mythology. I was teaching in mechanical engineering, structural mechanics, and one of the things that are very important in structures in Greece is the seismic problem, the earthquake problem. And there were many devastated earthquakes in Greece that caused a lot of trouble. One of them is the Kalamata earthquake, but all of them caused a lot of damage and casualties. The Kalamata earthquake was famous because it really devastated the city. If you see the map, the earthquake map of Europe, then we are safe. But if you see Greece, you cannot be safe anywhere in Greece. So it's a very important problem, and most of the research has been directed though to civil infrastructure and buildings, and we are quite experienced in that in our country, not only in universities but also the practicing engineers. But being in mechanical engineering and having the background in pipes and tubes, etc., my question was what may happen to an industrial facility or to energy infrastructure in general when the earthquake comes. Just a few months after I was appointed, there was a very bad event in Turkey, the Kocaeli earthquake in 1999. Apart from 70,000 casualties, there was a lot of damage in the energy infrastructure, not only that refinery, but also in other pipelines, water pipelines, gas pipelines, terminals. And that was a milestone in seismic engineering because it motivated, it triggered a lot of research, and it was a good timing for me. The most interesting project that we have participated and actually coordinated was the INDUSE project funded by the European Commission with the RFCS program. And we had the honor to coordinate an international group of experts, a multinational, multidisciplinary group, and the main deliverable was the seismic design guidelines for tanks, pressure vessels, and piping. There was a lot of work, a lot of testing on critical piping components that has been performed in many places by the partners. Noel Hresnik was responsible for the elbows. He did excellent work in those elbows, and as you see in the next slide, that it was very important for our numerical tools. And also in our university, we did the work on junctions, branches. That was performed by Professor Philip Perdikaris and his team. And I would like to really thank him for all the contribution, not only this, but all his contribution in our research. His dedication to laboratory experiment was very essential for the development of efficient numerical tools. In the numerical part, the topic that we really tried to develop, and I believe that we still are working on that and will be working in the future, is a cyclic plasticity. It's a very difficult phenomenon associated with several strange phenomena, difficult phenomena to simulate and understand. We are based on the experimental data that has been available to us, and there was a PhD that has been performed by George Varelis, who is in the audience, and there is another PhD that is going on these days. It's going to finish within the year. And I think that combination between experiments and numerical work was very important for us to understand the physical phenomena. Another topic that was very interesting and triggered our research interest was the geohazards and pipelines. Pipelines are an elongated structural system, so there are two types of problems associated, two types of actions related to this pipeline in terms of geohazards. Is the wave effects due to body waves on surface waves, and also permanent ground deformations, which are mainly faults, landslides, or liquefaction-induced loading. We are focusing on the permanent ones because that's much more critical for the pipeline. The wave effects are not so important unless there are some special features that are outside the scope of this presentation. So the problem can be stated as follows. You have two parts of the soil, and this is a discontinuity plane, okay? And then one part of the soil is moving with respect to the other one. So if you have a pipeline crossing that discontinuity, because of this movement, the pipeline is deformed, and then the question is your pipeline safe? To do that, the first step is to calculate the forces induced by the soil to the pipe, and this is what we call strain demand. And the main feature here is the pipe-soil interaction. So in that strain demand, we had a project also funded by the European Commission, and we also, the coordinators, coordinated again a multidisciplinary, multinational group of experts, and the target was to develop design guidelines for those steel pipelines in geohazard areas under permanent ground deformation. The most important contribution was were the numerical models that we developed. These models have been developed in cooperation with my colleague Panos Dakoulas, a geotechnical engineer, and we have also had a good student, Polynikis, who is now working in Germany as a fine element expert. And these models were the first to address the problem in a rigorous manner, so we managed to have a rigorous approach and calculate with accuracy the actions from the ground to the soil. And that project, the GIPIPE project, gave us the chance to cooperate with the people in CSM, in Centro Sviluppo Materiali. They had excellent facilities in Sardinia, and we conducted actually physical testing to calibrate those numerical models. And we did testing with the interaction in the axial direction, in the transverse direction, very good comparison between our analysis and also the test results, those two curves. And also we did the ultimate test. It's a big test. This is outdoor, 25 meters long, and 3 boxes. And we can simulate by pulling the middle box the landslide or the fault action. See, there's a video. That is the test. The pipeline cannot show, of course, is embedded, and this is our numerical simulation. I'd like to thank all the team of CSM based in Rome and in Sardinia, and also my student Gregory for this numerical simulation. The other topic I'll be talking to you is line pipe manufacturing. So it's the manufacturing of a piece of pipe. And of course, this is mainly a mechanical engineering topic, but I think that's important for structural engineers, because as a friend used to say, a pipe doesn't come from heaven, somebody has to make it. So the method that you choose to fabricate a pipe is very important in order to measure the properties, the final properties of your pipe, and that affects also your structural performance. One way to deal with this issue, I mean, one way to manufacture pipes is the spiral method. You start with a steel sheet that is in a coil, and then you de-coil that, you make it flat, and then by bending that in an angle, and by continuous process, you form that pipe. We have quite some interaction with several manufacturers, and we are able to get all the information necessary in order to model that process. This is the de-coiling, also the spiral bending. And if you have this model, and this is a nice video that my students have prepared, you have a very powerful tool so that starting from the properties of your coil as received from the steel manufacturer, then the pipe manufacturer can predict the properties of the pipe. And that is a powerful tool that can be used for optimizing the manufacturing process. We use that. This is an example that we compare our predictions with some data that have been given to us. We're able to predict also anisotropy, because if you take a piece of pipe in that direction and you test it, and another piece of pipe in that direction you test it, then you have different properties. And that's because of the manufacturing process mainly. Also, if you use that information, you are able to predict the mechanical behavior of those pipes under extreme loading conditions. And this is a test that has been successfully simulated. The test has been performed by Salzgitter management. But spiral is not the only method to manufacture pipes. We can manufacture pipes starting from a plate, and then by using some dies, you can make that round and then weld it and then make it round. So these are two methods for longitudinally welded pipes, the UOE and the JCO. UOE is very popular in the University of Edinburgh, although it doesn't mean University of Edinburgh. Those UOE means the U, the O, and the expansion, but it's just a coincidence. We have also contact with pipe manufacturers for simulating that, and this is a simulation of the JCO pipe. There is a current work that finished a few months ago with those students working. There is a PhD pending, but also there is a good cooperation with Corinth Pipe Works, a major pipe producer in Europe. I'll show you this process in finite element simulation in a nice video. First, you crimp the edges. Then there is a punch that is punching your plate in several places. So gradually you make it round, but first you make it take the shape of a letter J, so that's J there. And then you go on the other side and you continue punching. Takes a little bit of time. And continuing that, you make it look like a C, so that's a second letter. And then there is one in the middle to make it O, and then the punch goes away, there is a welding, and then there is expansion. You need to expand that to control the shape and avoid any out of roundness that is very difficult to be welded afterwards. So another project that I will present to you is called line pipes. These are pipes that are actually a very promising product for to resist internal corrosion. And this is actually a double wall pipe consisting of a corrosion-resistant thin wall liner fitted inside the carbon steel thick wall outer pipe. So this is the carbon steel and the stainless steel. And then if you bend it altogether, then you see nothing from the outside because it's quite thick, so nothing really happens. But the thin wall, which is inside, is also bent, and then you can have those buckles under confined conditions. It's a formidable buckling problem, shell buckling problem. We developed some numerical tools to investigate that, and our work was quite pioneering because we managed to show all the buckling bifurcations that happen there, and we got very good comparison with experiments, not only in shape, but also in the length of the wavelength and also the evolution of the wrinkle height. Another topic that we are very interested in is structural stability. This is probably more theoretical than the other ones, but it's a continuation of the work that I did in Texas, and there were 2 PhDs that have been given so far. This is buckling of elastic cylindrical shells, and one of the major things we investigated here was the transverse isotropy of those tubes, though you can consider those being fibers. And then we investigated the buckling shapes and all the post-buckling behavior of those cylinders. And then we extended this topic with our computational techniques to thick-walled tubes, and we investigated issues like buckle localization and secondary bifurcations in the plastic range, and we compared very well with tests by Professor Kyriakidis in Texas. A topic that has a lot of interest in many countries is what I call pipeline integrity, because it is related to aging pipeline infrastructure. And in that topic, we investigated the integrity of pipelines, existing pipelines that have local wall distortions, either from dents or from buckles. Of course, there is no loss of containment immediately, because the steel material is quite ductile and the containment can be sustained. However, if you operate that, the operational load gradually can cause fatigue in those locations because of strain concentration, and this is a threat for your pipeline. So we conducted experiments in the lab together with Philip Perdikaris again. And there was a PhD on this. We got also funding from Europe and also national funding, and we developed fit and for purpose methodologies in order to assess the structural integrity. An exciting topic that I will present to you refers to water pipelines. These are pipelines that have some particularities, and it's a work that started quite some time ago and it's still continuing. It's very interesting. It is mainly related to the steel water pipeline community in the United States. And my interaction with that community started in previous decades. This is Bob and George. They're also here, and it's very happy to have them here today. Very good friends, and we work together in a project I will present to you. I'm very proud, in 2013, in a seminar that has been organized by Northwest Pipe, I'm very proud being close to Bob. Bob is an expert in pipeline engineering, in water pipelines, and a well-respected engineer in the United States. And these are Brent and Rich from Northwest Pipe, 2 people that wish to be here but they couldn't, but there are people that we cooperate in a project that I will present to you. So my first interaction with this community was the ASC Manual of Practice 119. It's a famous one because it is being used by many people, many practitioners, many pipeline engineers in the United States. And this is a work that it's a document that is based on the work of Professor Reynold Watkins from Utah State University. Professor Watkins is considered to be the Pope or the Patriarch of steel water pipelines in the United States. This is his dedication, and we had a great team here that Brent and Bob and George were also in the team. And we developed that very important document. And also, it's my honor to have interacted with this famous professor. Nowadays, we continue this cooperation with the steel water pipeline community in the United States in the strength of welded-lap joints. These are joints that are totally different than the ones that we have in oil and gas. And it's very simple to contract. You just need to expand the end of your pipe, and then you insert the other one and you do those 2 welds, either on the inside, the outside, or both ways. And this is a work that we conduct with Northwest Pipe and Brent Kyle and Rich Milke, and also Bob is supporting this work with his experience. The major problem here is that although those joints have been used for a pressure design for a very long time, and everybody was very happy, when it comes to geohazard, where your pipe is really bent in extreme conditions, there was always a concern how those joints behave. So that is the major topic of our investigation. So we developed numerical tools, and we are based on experimental data, limited experimental data, in order to understand this behavior. Actually, there are locations that are really prone to buckling. Therefore, we need to be very careful about the integrity of the pipeline, especially at those locations. And there is another cooperation also with HDR, a big consultant company in the United States, with David McPherson and John Platschmeyer. We are developing, they have developed a pattern, and I am helping them to verify that is a strengthening bell that goes outside your inner bell and strengthens that, and that could be very useful in terms of geohazard action. The final project that I will present to you, and started a few years ago in my old university, is tubular structures, but mainly for offshore wind energy production. The first project we have from the European Commission refers to fixed offshore platforms, jackets for wind energy. This is not something new. Many people are using those for supporting wind towers and the wind turbine. However, the purpose of this project is to develop optimized solutions to support 10 megawatt wind turbines in the water depths that are not really deep. We're talking up to 80 meters, so it's shallow water basically. But the target is to do this optimization in order to reduce the cost of the structure, and that is an important part of the total cost, and that will be very important for the competitiveness of the wind energy. We are working on the connections, and also another issue is the foundation of those. We are doing mainly numerical work on validating, these suction caissons foundation, which is rather new with respect to the old type of foundation with piles. Piles have been used for many years, but for some reason this one has some advantages. But there are some open issues to be solved, mainly because of the cyclic loading due to the waves and the interaction between the caisson surface and the soil. So that will be an important thing. Maybe by the end of the year we will have some new results. I think the most interesting results, project is the REFOS project. It's also sponsored by the European Commission, and it is a renewable energy floating offshore system that combines wind energy with wave energy. Actually, those cylinders have air that is compressed because of the waves, and this compression, actually, this cyclic compression can really generate wave energy. So it's the OWC concept, and that is under investigation. It started about 1.5 years ago, and I believe that by the end of the project we'll have an efficient solution for that renewable energy production in water depths that are about 150 to 200 meters approximately. It's a concept that has been developed by Athens and Professor Mavrakos, and we are happy with this cooperation. From theoretical point of view, we are continuing our work on fatigue of welded connections. One methodology that we are trying now to develop is the cohesive element methodology. Of course, numerically, there are many people working. What we are trying to develop also is, together with the numerical methods, we are developing some key experimental testing in order to have a systematic procedure for calibration of the numerical models. So the final destination is Edinburgh. I'm here since August 2016, to be more precise, September 2016, and it's a fascinating place. Of course, it takes only 4 hours to fly from Athens to Edinburgh. It took me 49 years to come here, but I think that the trip was quite interesting. But also the destination is very interesting, and I'm very, very happy to be in a group of people, very good people. Actually, we're 12 people that are related more or less to structural engineering. So there is a lot of engineering expertise in our department. There are also other people that are related to structural engineering in other departments, like the mechanical engineering department. We are working on several topics. You see expertise ranges from buckling, fatigue, impact, corrosion, fire, earthquakes, sea waves, all the bad things that can happen to your structure. So we have quite a good range of applications, and also there is a structures lab that help us doing experimental work. We are also working on amending these capabilities. And also we are associated with several laboratories in the university to complement those capabilities. Recently there is we cooperate in the construction of the new structural composite research facility together with Composite Materials Group and Professor Coher O'Brady. It's a facility that will allow us to test in fatigue very efficiently elongated structural components. Just some slides for the research activities in structural engineering. The research activities that we plan or already have started working on in Edinburgh. We will definitely continue our work in cyclic loading. Cyclic loading is very important for the integrity of metal structures, steel structures, and we continue the development of numerical models for simulating all these interesting phenomena: low cycle fatigue, ratcheting, material degradation, distortional hardening, etc. And there are many applications, many industrial applications that are very important, not only to keep us close to the physical problem, but also to have funding opportunities. We definitely continue working on pipelines. Our work is driven by mainly two challenges. The first challenge is the installation of pipelines in deep water, in the water depths that exceed 1,500 meters. And also the other challenge, the construction of pipelines in geohazard areas, mainly in areas of important seismic activity. There is a PhD that started a few months ago on line pipes, a topic that I presented to you before. In particular, we are interested in another method of installing pipelines, the reeling method. In that method, you take the pipes, but not onshore, but offshore. You take them onshore, so you connect the pipes together onshore, so you form this big spaghetti onshore, and then you spool that around that reel. And then when you go with that ship offshore, then you unspool and you launch the pipe, and that's where you install your pipe. And what we are doing in this PhD is to investigate what is the mechanical behavior of line pipes, double wall pipes that are installed through that method. So it's a formidable problem that combines buckling under confined conditions and also cyclic loading and other related phenomena that we discussed before. We continue our work on geohazards and infrastructure. That offers a lot of opportunities. It's a multidisciplinary topic that involves structural engineering, mechanical engineering, geosciences, and sometimes social sciences. Two projects, two activities. One is to continue our cooperation with the steel water pipeline community in the United States, and especially to see the integrity of those pipes under seismic action. There is a cooperation with Northwest Pipe and also with HDR. With Northwest Pipe, we recently conducted a very innovative testing in Adelanto, California, in their facilities. And we plan to work on those, calibrating numerical models and understanding the phenomenon much better. And we hope this work will be part of the new MOP, the Manual of Practice, that ASA is developing for seismic design of water pipelines. The other activity refers to the MECOS benchmark, which is an activity under the auspices of the OECD. And there is an international group of people that I'm part of those, and we are working together in order to develop design criteria for the seismic design of piping systems, mainly nuclear but also industrial. There are some tests that have been performed by Professor Reddy in Mumbai, and based on those tests, we are benchmarking numerical models and methodologies. Fatigue of welded connections, it's a topic that is traditional, and we are trying to develop more tools in order to investigate new aspects. We are particularly interested in the extreme loading of welded tubular connections, and in particular with low cycle fatigue failure modes. The motivation for that is the use of high-strength steel in offshore structures for renewables, and that is part of the general consideration these days for reducing the cost in those structures and make that renewable energy more competitive. There is a PhD by Kostis Hadjiouanou, is here, and this supervised by Yuner Huang, and I'm very happy to be part of that team. That combines experimental work in our lab and also advanced numerical tools. Condition assessment. That's a very important topic for energy infrastructure system, for infrastructure systems in general. The motivation is, and the buzzword here is the aging infrastructure. And people have to realize that when there is a project of constructing an infrastructure system, for example, a pipeline or a facility, then in day one, you have the politicians there, the inaugural day, you have the media, the local people, everybody is happy. But after that, day two, day three, under operation, then those assets tend to degrade. And several components in that infrastructure in our countries have reached their design life. I mean, they're operating for 40 years, 50 years, even more. And the question is what to do with them. So in order to decide, you need to have accurate methodologies so that you can assess residual strength and predict the remaining life for safe operation. So we are following an integrated approach that starts from inspection and goes up to decision making and strengthening actions. Of course, it's impossible for the University of Edinburgh to cover all that expertise efficiently, so we are talking to other people that are experts. So we are forming a strong team of experts from other universities so that we can really tackle the problem in that integrated way. And finally, I'd like to say something about structural stability, which is a topic of very significant for many applications, many structural applications, and not only structural. There has been a long time tradition at the University of Edinburgh. This tradition comes from the presence of Professor Michael Rotter, who is here in the audience. Michael has been a person that is famous for his research, but also a very good engineer, passing all that research experience into the design recommendations. And this tradition is something that we would like to continue. Looking around, unfortunately, you see that all these experienced people like Michael, all these experienced bucklers, are very few. So the question is, what's going to happen to structural stability when all those bucklers actually cross the bar? So I think that this legacy has to be maintained, and we have a very important opportunity here because of this legacy and with my expertise in order to develop these structural stability concepts not only in education but also in research by developing computational tools, doing key experimental work, and the most important is extending that expertise to innovative areas like nanomechanics or biomechanics. So that's the most difficult part. And it's difficult because I have been working with many people, and it's difficult in 1 or 2 slides to put everybody there and thank everybody, but I'll try to present that in the most compact way that I can. So I'll start with my students. I've been very happy in my career to work with very good students. There is a list of the PhD students. George is here, he's the first in the list. And thanking George, I'd like to thank all my students because without their contribution, I wouldn't be able to talk to you today. I'd like to thank my advisor, John Dasoulas. He was a person that taught me a lot, and his dedication to high quality research was very important for me. Manolis Papadrakakis is a well-known person in structural engineering internationally in computational mechanics. He was my advisor in my diploma thesis in Athens and very supportive in all my professional steps. Dimitri Beskos in Patras, I met him at the age of 16, and he was the one that persuaded me to follow a civil engineering career and also make use of the structural engineering tradition of the family. Noel Hresnicht, we did a lot of work together, and Noel his dedication to quality experimental work and also his understanding of physical problem was very important for us to develop efficient computational tools. Jaap Wardeneer, professor at that time in Delft, he gave me the opportunity to go to Delft after my military service and actually make an important step in my career, and has been very supportive in all my steps all these years. Stelios Kyriakidis in Texas, famous professor, famous buckler. He's well known in buckling problems and also in pipeline mechanics. His experimental work has been very inspiring for not only for me, but also for my students. Michael Rotter from Edinburgh. We hope to continue his legacy and his very good work. Also, I'd like to thank many people from the University of Thessaly that I made all those projects. And we had a wonderful team in mechanical and civil engineering, very good colleagues. But among them, I'd like to mention 2 names. One is Philip Perdikaris. He was the director of the lab. So he did a lot of tests that supported our analysis. And without his contribution, I think we wouldn't get so efficient models. So I'd like to thank for his friendship and contribution. And also Ioanna Haralambous. She's our administrative manager. She is the person behind all those projects in terms of administration, very important task dealing with all the bureaucracy in the university, in Athens, in Brussels, and wherever we had some projects. Of course, apart from these people, there are many people in European projects, and all those are cities that I have visited during these last 10 years. And there are more than one person that we cooperated in some of those cities. But most of all, I'd like to thank Giuseppe De Mofonti from Rome. He was the one that first understood that we could contribute and gave us the opportunity to participate in those projects. Finally, I'd like to thank all my collaborators and friends from the United States. Brent and Rich from Northwest Pipe, Bob and George that are here today, and David and John from HDR. And of course, the Karamanos family. This is a picture with my parents that are here today, and also my sister's family. And most of all, I'd like to thank my wife Penny, Io, my daughter, and my son Tony. I miss them a lot. They couldn't be here today for all the logistic problems, but I really miss them, and I dedicate to them this presentation. Finally, I'd like to thank all the people at the University of Edinburgh for their support. I'd like to thank the principal and also the head of school for their continued support, and also all my colleagues, academic staff, technical staff, and administrative staff for their support since August 2016 that I'm here. And of course, Louise, for organizing this event. Thank you, Louise. And thank you, everybody, for coming to this lecture.